page and see if it's working. This is a time when I should make funny faces. Does anybody see us?
And then the webcam breaks because it couldn't handle it.
This live event will begin.
Yeah.
Okay, so that's good news. That's good news.
Man, that screen took a couple of hits.
This is just the screen. The screen itself should be fine. It is. It builds it off the check. The screen is completely intact.
I put on the screen.
Amazing.
Right. My bad.
Couple more months.
Is it recording already?
It should be. Does it come up for you?
Try it again. Try going in there again. Maybe it's needs a little encouragement.
Oh yeah, there we go. It is.
It is. What's the lag?
I'll tell you in a minute. Possibly two.
Okay, so that's already quite a lag, isn't it?
Yeah, it still hasn't shown up you doing this, so it's probably going to be a bit.
30 seconds.
And I think it just stops. Actually.
No, it's still.
It's just choppy.
Well,
Yeah, so like, I think just now, it was you acknowledging, oh, it works.
Okay.
Yeah, there you go. There you go. Finally showed up you doing this. So like 3 minutes delay, maybe?
a minute.
I don't know.
A minute to a minute on the bit. Yeah.
I'm what am I?
Okay, well.
Yeah, it was like,
Okay,
it felt long.
so I want to come back. I need to go get
Should have had- It's fine. It is what it is. It's fine. Did anybody else finish the assignment? The project?
What's on the exam? I actually kept it this
But
time.
did you cry over the exam?
No, it's just the rain.
Sure.
I almost cried. This was so absurdly easy that
When you get there, it's so,
so like this one
that's awful. That's right.
implement the function using the decoder show and navigate. So all I did was 0 output, 2 output, 5 and 6 and put it into the navigate. That's it. That's the answer.
Done. Finished. Good.
This one is the same. This one I didn't know what to do, so I just input the 1, the 2, the 5, and 7. And that's what had me worried. I was like, I can't be doing this right. This is too easy. I was literally just drawing wires into that. And no, that's it. That's right. No. Sorry.
You check your book, for example?
Nope. I'll find out. There's nothing I can do about it now.
Right.
I'm gonna need to press
Just make that paper a little bit more sloppy, right?
Yeah, exactly. If I'm gonna find out that it's wrong, let me do it when I get the break that.
Right.
Right now, what I'm gonna do is focus on the one fact that it's a little bit. My objective is to get it up to 70 or 64. I actually think I can, because there's just one question that I really deserve a lot more points on. Like, that's one that I will. Like, obviously, I don't mean I'm not going to be very heated, but that's one that I'm going to like argue over if they refuse to. 7 will get me close to a B. Probably
Yeah.
7.
Just for you. You can do it.
Any project?
No, not yet.
I can work on it.
Right now?
What? I don't really have enough juice in my computer to get that.
Or we're all right. It's not like I got to sleep or anything.
It's for the week.
No, but it's all right. I don't have any exams tomorrow, so I really don't.
And you have it on Friday.
Yeah, Thursday and Friday. So ideally, as long as I get sleep tomorrow, that would be the objective. So hopefully, we're hoping for that. That's what we'll aim for. We'll aim for getting some sleep tomorrow night.
Good luck.
And then maybe get some sleep Friday night and Thursday night as well. If we can do that, I'm aiming for 6 hours, but that's a crapshoot. That's the ideal. We're looking more like maybe 3 to 4.
I think we'll get this done.
But then, after this week is over, that's it. I pretty much retire from school until next year.
All right.
Just stop doing everything. No, we already have our next homework assignment for this class. It's due next Wednesday.
The teacher needs computer.
We have to implement. We have to do the same thing we did with the bubble sort and all that. So we're doing merge.
Yeah, it's for you guys to see what the difference in speed.
Yeah, hopefully these will actually be able to handle larger data files.
And tip search. Tip search would be nice.
That's
I wonder if there's a tip search implementation.
Will you give me a hand, please?
It's a big old page.
A natural like data set assets. That has to do with growth. With the actual this constant.
President, what could you tell us about Tim's?
What?
Tim?
It's Tim sort
Tim's.
from Python. It's sorry, algorithm that was implemented in Python. It's like 2002.
I know nothing about it. You should tell me about it.
I'm not familiar with it, but present.
I mean, I read about it on Wikipedia and I wrote it. It was interesting. If I'm not mistaken, it's like merge sort and insertion sort together, working together to make it a little bit faster. So the idea is that it defines the runs in the data set that you pass into it. So the things that are already stored, and it at those points, then just merges it and uses insertion sort for some other reason that I don't know about. I thought it was an interesting one right here.
So the only problem is
Oh no, just like. There you go.
The best case is that
Alright.
every case is in login. The best case.
in principle have more people viewing than we have
Present?
present.
The maximum was 10 people.
Not on Hangout Air. On the static Hangout it is 10. Now there, there's no limitation. It's like how many people can watch a YouTube video at the same time.
Right.
In principle, that should be.
You have a viewer count for the user?
It says it's been fluctuating, so it's probably somebody's having a problem. It went up to 9, it's down to 8 now.
That's why I'm from.
Well, you're right, it is.
That's all it's.
You want to use certain arrays.
Like I would be going to jobs that
Android platform.
How does it identify a run though?
So it's checked, a run is identified by a sequence that's already suited. Well, it checks the first number, then it checks if the next number is bigger than the last one. And if it is, continues, and then it checks if the next number after that one is bigger than the previous. So it keeps on doing this, right? And when it finds one that's small, it's better than the previous, so it gets it off there. And that's your first one, and it continues on to the process of the next one.
Oh,
And I don't know what it is.
So that's sort of, that's how.
Measuring all my customers. But I use it.
That is better than the pivot.
There's not, if I don't, no. Can't do that unless I go.
Okay, it's 7 minutes past 8. Let's get started. I'll begin with a discussion of questions on the project. Any questions? Please.
In the first section of the project,
Yes.
it asked us to define the use cases.
Yes.
And then in the second part, it said to define user scenarios. Are those like two different things for the same thing?
The first part of the project should not ask for use cases. It should ask for describe in detail the problem statement. Because remember, I gave you a problem statement at a very high level. I want you to flesh that out and define the level. But to answer your question, user scenarios are part of the use case, yes. So, I would say for this purpose, they are synonymous. Okay. Other questions? Please.
For the submission, do you want the code online and the.
Exactly as we've been doing for homework. So I do need the code submitted through Sakai, so we test it, we run through, turn it in, so on and so forth. Okay. And I want a hard copy of anything else. And in this case, there'll be substantial amount of the hard copy.
Are you going to be available after this lecture?
Briefly, yes, I will. Yes. How long do you need me for? Okay, let's stop. Let's get started. We can see how long we can go. We can do one thing. I'm going to go for a run after this. We can talk while I'm running.
I would definitely do it.
You can get it for an hour.
Oh, you're going for a run afterwards?
Yes.
You're not going to be able to go to sleep early.
Say again.
You're not going to be able to go to sleep early.
I'm sufficiently tired that I fall asleep straight away.
Oh, really?
Okay. Okay, let's get started. In that case, if there are no other questions. We'll talk more about this tomorrow, but you are aware there's, remember we have an exam on Monday, right? And then I did the maths. We're left with 5 classes after that. Just to tell you what we're going to do is we're going to really do 2 topics. Well, primarily 1 topic after that exam, that's graph algorithms. And variations on graph algorithms, we do some tables. So that'll be the 4 or 5 lectures after the exam. Tomorrow we'll try to do in a single lecture, we'll try to do heaps. Just a very quick question, how many of you have worked with heaps or know about heaps? We did not do heaps in pm1, I gather.
I think you mentioned it like for 1 or 2 lectures, but we didn't work with it. Okay.
Good. So we'll work with it this time. There'll be homework on heaps and binary search trees. Okay, let's get started. I'm going to start sharing my screen. Give me a second. Okay. Hopefully, those of you who are seeing this streamed will see this. Will see the slides as well. Okay. It'll help if I project there. Cool. That is it. Okay, let's go a second. So that's good. Great. Let's get started. Trees. I think we touched briefly upon trees just in less than a couple of minutes. We talked about how trees are going to be the first ADT that we're going to discuss that is not linear, i.e. is nonlinear. And the important thing about trees is they help us capture various relationships and primarily hierarchical relationships, as we'll discuss. The other attribute was that we don't insert or delete trees based upon positions, even though we talked about linear ADTs yesterday, and there was an exception to the linear ADTs in terms of all of them were position oriented, with the one exception of a sorted list. What we'll find here is that even though some of the trees that we will work with will be about value, we won't insert, will be about represent relationships. We will not be using positions to insert the values. In many ways, the nonlinear setup and is a way of capturing the fact that these are not position oriented, but the first nonlinear value-oriented ADTs, and hopefully this will become clear in a few minutes. We're going to discuss two types of trees. The first is the ADT binary tree. Again, something which should at this stage be conceptually quite simple. A very powerful ADT in of itself, used for many different aspects. But what we want to do is to try to understand how we might be able to use it for binary search trees and the many powerful operations that binary search trees provide. So let's get started with some background. As mentioned, trees will help us represent relationship between items. Importantly, trees are hierarchical in nature. Although we call them trees, they in many ways represent a parent-child relationship between the nodes in a tree. And we'll see some examples of trees in a few seconds. Whether you call them parent-child relationship or whether you generalize that to ancestor-descendant, different ways of capturing the same concept. The lines here don't really have any value of physical interpretation. The lines, however, are called edges. The lines between nodes will acquire significance when we talk about graphs, which we will in a weeks' time. Importantly, a tree is comprised of subtrees, and a subtree in a node is any node in the tree together with all of its descendants. Okay. So let's look at some very simple examples. You can see the tree on the left-hand side as arguably a very, very simple representation of a tree. Let's look at the relationships that this tree captures. Again, very simple, very obvious. But since some of you have not seen trees or worked with trees before, you'd say that A is the parent of B and C. You'd also say that A is the ancestor of D, E, and F. You wouldn't say parent, but you would say ancestor. Similarly, B and C are children of A, but D, E, and F are not children, but they are descendants of A. So you see the very obvious, almost trivial hierarchical relationship. And so if this is a tree, you can see that the tree on the right-hand side is a classic example of a subtree, in the sense that it is a tree in of its own right, but it is a tree that is part of the larger tree. Nicholas?
I'm sorry, you may have already said this, but is this lecture on the exam for Monday?
Yes, today's lecture and tomorrow's lecture will be on the exam. So some of you asked me this question. I mentioned this already. Everything we do till tomorrow's lecture will be on the exam. But that's why I mentioned we'll do heaps tomorrow. We'll do trees today. So it'll be sorting, or I should say algorithms, sorting, trees, and heaps. 4 topics.
But like not the data structure stuff. Like...
Nothing before algorithms. Remember, we started algorithms maybe 2 lectures before the first exam. We had 2 lectures of algorithms, but they weren't part of the first exam. So we will go back to that. And those were the basic.
So algorithm sorting trees.
Okay. So again, here's just another, this was fairly abstract. Here's a more kind of specific example of how a tree might capture a hierarchical relationship. I mean, it's all quite obvious. Some pseudo company, you can see that there'd be director of sales, director of media relations, reporting to a VP, reporting to a president. You get the idea by now. Or this could literally be a set of specific people that represent. Oh, actually, one second. That has more meaning, which I'm sure some of you will catch. The one on the right-hand side. Okay. So a general tree, although we're going to talk about binary trees, I want to kind of motivate the concept of a tree as a general concept. And really, a general tree, as shown here, capturing the hierarchical relationships, can have any node can have a large number of children or a large number of descendants, thereby generalized to a large number of descendants. Right? It can have, therefore, so what we then move on to is, say, an n-array tree is defined as one where the root or any parent, any node has at most n children. I repeat, an n-array tree is one where a node has at most n children, right? And again, you can therefore generalize this to the possible number of n-array subtrees. But the real point of interest is binary, so a specific case of n-array, where n is 2, and therefore binary, where a single node at most can have 2 children. And you see the similarity between, or you see how we've gone specific from general to n-array to binary. Okay, so here out onwards, we will be focusing on binary trees. And you can see once again, just for completeness, let's notice that each node has at most 2 children. Quite obvious. Just wanted to call that out. And here's another specific example of how, in addition to hierarchical relationships, binary trees can be used to capture algebraic expressions. We'll come back to this at some later stage, but here's an algebraic expression A minus B, and you can capture this in a node here node there. And so if you remember the concept of traversals, we've done that in the past. So if you started traversing from A to this, from this node on the left-hand side to the center node to this node, you can see how these relationships can be, how the tree can be used to capture algebraic relationships and expressions. Okay. So we'll spend a lot of time talking about these, but just about binary search trees, but just to get the concept out. A binary search tree is a type of binary tree, but it has certain additional properties. What are those additional properties? The node of any binary search tree has a value such that the value of the node is always less than the value of nodes in the left subtree, but greater than the value of any node in the right subtree. I repeat, a binary search tree is one which such that for any node, the value of that node is greater than all the values in its left subtree and less than all the values in its right subtree. I apologize. I think I said that the other way around the first time. I apologize. And again, the same recursive relationship holds. You can take any subtree and these values will hold. Right? Go ahead.
I remember something like from pm1 where like when you're doing trees, they have to be like balanced, so like a root.
We're going to talk about that in a few minutes. The concept of a balanced tree is very important. We will spend time after the second exam talking about a fair number of algorithms devoted to keeping trees balanced. So in a few minutes, I'll first describe what's a balanced tree. I'll also give you counterexamples of balanced trees, and we'll see some examples of both. Right? And then hopefully before the end of this lecture, you'll be able to appreciate why trees become unbalanced. Okay, so hold on to that thought. And so here's a binary search tree. Let's just talk about this tree. Let's understand it carefully. So remember, the values are very important. We'll introduce a term called partially ordered, and then we'll come back and visit this term when we talk about heaps, where we will talk about something called weakly ordered. I'd like you to compare and contrast binary search trees and heaps, but that's for later. So again, you know the basic property of binary search trees. Let's just investigate whether this tree satisfies those basic properties. So what's the basic property? Any node is greater than all the is less than all the values on the left-hand subtree, and is greater than everything on the right subtree. Okay. Again, I said that the wrong way around. I apologize. A node is greater than every sub value in the right subtree and smaller than every value in the. Okay, I guess I should have had another cup of coffee.
Less than on the left.
Yes, thank you.
See, so Jane is smaller.
So one last time.
Oh, yeah, okay.
A node is greater than all node values on the left subtree, and it is smaller than all nodes in the right subtree. Okay, don't make me repeat that again. I said it right this time. Let's go with that. Okay.
Jane before Tom.
Exactly. So that's what I want you to verify. That what's the left subtree that below Jane? It's Bob, Alan, and Ellen, and you can see alphabetically speaking, B, A, and E all come before J, i.e. less than J. Tom, Nancy, and Wendy, that's T, N, and W, are greater than J alphabetically. So you see, and then that's not enough. Let's look at the subtree captured by Tom, Nancy, and Wendy. Right? T is now the node of the tree, and you're looking at this subtree. Okay, that's Tom, Nancy, and Wendy. What happens here? You can see that Tom is greater than Nancy, but less than Wendy. So you see that hierarchical structure, that recursive structure being preserved. Is everybody with me? Sorry for that goofiness earlier. Okay, so now coming to appreciate some properties of trees so that we have a vocabulary that will allow us to, well, compare and contrast trees, but also help us highlight the primary properties of trees, one of which will be the height, which in turn will lead us to the concept of balanced or unbalanced. So a series of slides with some basic terminology. They're all very simple, but let's walk through them. Let's begin with the definition of the level of a node. So now we're not talking about tree property, we're talking about the level of a node. So if you have any tree, the root of that tree is assigned a level 1, right? So for a given tree that you talk about, there's exactly one and only one root. Now, it may be that that tree is another tree's subtree, okay? But for the moment, you're talking about a tree, and for the tree, there is a unique root, and that root is a node which has a level 1. Okay, so I just wanted to make sure you appreciate the fact that a node's level is set to be 1 if it is the root of a tree, even though that tree, when you think of it in a larger context, maybe this node may be a subtree, and then it is no longer the root. It then has another level value of a level, because now you're talking about another tree. Does that make sense, everybody? Good. Okay. So if n is not the root of a tree, its level is 1 greater than the level of its parent. So we can go back for a second and look at this. And you can see here, what question?
I think you're right, explaining.
Okay, so if I don't, ask me. So you can see here, what's the root of the tree? Jane, right? The node value of the root, sorry, the level value of the root is 1. Okay, what's the level of, let's say, Bob? 1 plus the level of its parent, which in this case was Jane, and therefore 2. And led by extension, what is the value of the level of Ellen? 1 plus its parent, because Ellen's not a root. Therefore, it's 1 plus Bob's level, which is 2, therefore 3. Okay. Have I answered your question to some extent?
Yeah.
Okay, thank you. So we've got the notion of a level. Now let's talk about the height. Again, level works on a node, height works on the tree as a whole. So the height is a property of the tree. Level is typically the property of a node in a given tree. The different ways of defining height of a tree. One way, which I've not written out here, can be defined as the number of nodes on the longest path from the root in that tree. Or I should say that I think from the root is redundant. The longest path in a tree and the number of nodes encountered is the height. We'll see some examples. So hold on to that definition. Another way of looking at or thinking about the height of a tree is that if a tree is empty, you define its height to be 0. If a tree is not empty, its height is equal to the maximum level of its nodes. So let's go back to this. So clearly this tree is not empty. What is the maximum value of the nodes? We calculated that to be 3. Okay, we didn't calculate that for all of these, but you can see by visual inspection that it would be 3 for all of them, right? And therefore the height of this tree is 3. Now let's invoke the definition that I said, but I didn't write. Also the number of nodes encountered on the longest path. Right? So that's also 1, 2, and 3. Okay, so you've got 2 definitions of heights. There's a reason why we choose this definition, because it is setting up, it is amenable to a recursive, to a hierarchical definition, right? And it's going to be prove to be very important. Okay, so let's again look at some examples very quickly to just solidify these concepts in our minds. So let's ask a few questions. two questions for each of these trees. What's the height and what's the level of the lowest node? Okay, so first of all, what's the level of node D? Who's going to help me? Go ahead. And that is because?
Because its level would be one more than its parent.
Right, and its parent is B, which has a value
Of one more than its parent.
which is 1. Great. Simple, great. I just want to make sure. And therefore, the height of the tree here is also 3. Okay, so we've done this. Now let's look at the slightly more interesting examples, and I'll start off with this one and this one. So first thing you observe is that these trees look very different, right? But let's calculate the height of this tree. Let's go straight to the height of this tree, right? And this tree next to it. So what's the height of this tree? Sorry? 7. Does anybody disagree with him? Does anybody agree with him? Okay, 2 people, 3 people, 4 people, okay. So yes, it is 7. So, and that's because either way, either definition, either you say the number of nodes on the greatest path, well, in this case, is exactly one path. So 1, 2, 3, 4, 5, 6, 7, right? And what's the height? Oh, sorry, what's the level of this node? Say again? Exactly, right? And here as well, you can see that, well, in this case, is exactly one path, and that has a height or a level 7, has a height of 7. Level of the last node, G is 7. But compare this. It's got the same number of nodes as these, if you look, because it's A to G, right? Same number of nodes, but come on, somebody tell me what's the height of this tree? Please. 5. Exactly. So you can see what's happening here, the same number of nodes, but they have different, if you will, structures, and thereby one measure of capturing the difference in the structure is represented by height, right? So here you have a height 5, here you have a height 7, even though both have the same number of trees, same number of nodes. By the way, just for completeness, this also has the same number of nodes, but as we discussed, has a height of 3. So number of nodes is 3, 7. Height could be a maximum height, in this case was 7. A minimum height in this case was 3. So we'll come back and we'll revisit this. But before we move any further, is everybody comfortable with the concept of height of a tree? And also the concept of the level of a node? Any questions? Please.
So there's nothing really different between C and D here, right?
Nothing really different between C and D here.
There is.
What's the difference?
Well, from A, it branches to the right, and then from B, it branches to the left, and from C, it branches to the right. Whereas in D, it simply branches to the right all the time. So if you were to represent it in a data structure, different nodes, you'd say that the right for A is occupied, but the left isn't. The left for B is occupied, but the right isn't, and so on and so forth.
That makes sense.
Say again?
That makes sense.
Right, but what's left and right? Go ahead.
I was just going to say that in D, every value is greater than the previous value, but in C, D is greater than A.
I want you, and that's why I paused for a second when you started answering.
Yeah.
These are binary trees. Remember that property was for binary search trees. Right? There is no relative ordering of the values of the nodes in this particular case because they're binary trees and not binary search trees. Okay?
That's right.
So in some ways you're right, but semantically I don't think, and yeah, it depends at what
When it
level.
comes to the height and the number of nodes,
Exactly, there's no difference. And I think that's, you have to establish what different based upon what. And if you're talking about height, then the answer is no, there is no difference. Is there a difference between left, right? Absolutely. Does that mean anything? Who knows? Does it say anything about the relative values? Not at all, because this is a binary tree. Okay? Okay, so now let's come to the concept of full, complete, and balanced trees. We've introduced the notion of height and level, and that's necessary to appreciate. So what is a full binary tree? Well, the name probably tells you what a full binary tree is. It's a tree that is full. So if you just, I'm appealing to your intuition here. Look at this tree, right? And look at this tree. You can see voids in this tree, right? You could add additional things to fill it up. Could you add any more nodes here without increasing its height? No. Right? So if you could add more nodes without increasing its height, that's telling you it's not full. Right? Similarly, left or right, you could add nodes here, you could add nodes here, you would not increase the height. Right? So before we get to the formal definition, I hope I appeal to your intuition of what would constitute a full tree. Full, the other three are not full. Now let's look at a formal definition of a full tree. First of all, let's take the base case. And again, it's important to appreciate why I present it to you in this way, because there's a deep connection between recursive relationships and trees. You may have already encountered this. If not, I'm sure you will. So let's do the so-called base case. If a tree T is empty, it is a full binary tree of height 0. Right? If T is not empty, i.e. there's more than one node, and has a height greater than 0, T is a full binary tree if its roots subtrees are both full binary trees of heights h minus 1. So first of all, do you notice the recursive nature of the definition? I hope everybody does. Right. Okay. Now let's look at what this means. Oops. So T is a full binary tree if its roots subtrees are both full binary trees of heights h minus 1. Right? So clearly you go on and on thinking. So you basically start with a tree of one node, which by definition is a full tree, yes. Then you want a tree of height 2, which would then require the tree to have 3 nodes. Right? And then you can now see what you have to do for a tree of height 3. You've got to have 2 subtrees, each of height 2, but must be full. And therefore, you see, I don't know if all of you will be able to see. I apologize to those for whom this is being streamed. Full tree of height 1, full tree of height 2, and a full tree of height 3 must have 2 subtrees of height 2, which are full, right? So that is a full tree of height 3, and then you can go on, and you can see that this is consistent with the earlier, slightly more informal definition that I gave you, that there is no more space to add a node without increasing its height. Okay, but the formal definition that you want to appreciate is this recursive nature. Okay, so that's full tree. Let's discuss what's a complete tree. A complete tree is one of height h, beg your pardon. It's important to capture the height as the defining feature, as a parameter, beg your pardon. It is complete if it is full to level h minus 1, okay? It is a full tree to level h minus 1. Note, where is in a tree, is the level the highest at the top or the bottom? The level is greater at the bottom, right? So a level h minus 1 is saying all the nodes except the so-called leaves, right? So a binary tree of height h is complete if it is a full tree to level h minus 1, and level h, i.e. the lowest level, is filled from left to right, okay? And we'll see an example of that soon. So in some ways, let me pop a question at you. Do you see any complete tree here? You say yes. Does anybody say yes? Does anybody? You say yes? Yes? And can you and yes, can you identify the full complete tree?
I'd say,
You'd say C.
no, A.
A, sorry. Anybody else? Complete tree? Come on, somebody at the back. Which is a complete tree out of these? Okay, A. Yes, A is a complete tree, and it also happens to be a full tree. So that's another point I wanted to make. A full tree is a complete tree, right? What's the definition of a complete tree? We just talked about this. It's a full tree at h-1 level, and every node on level h, the nodes are filled in from the left side. And you can see that this is, first of all, a tree of level 3. It is a full tree up till level h-1, that is 2, right? And every node at level 3, or the nodes in level 3, are filled in from the left side. As opposed to if you had, let's say you removed this node, then you'd have nodes being filled in from this side as well as this side. And therefore, if I removed F, it would no longer be a complete tree. Obviously, it wouldn't be a full tree, but it wouldn't be a complete tree of height 3.
So if you remove G and E, it will still be a complete tree.
Not G and E, just G. If you remove E, then it will not be a complete tree. Okay? So now let's look at another recursive definition of complete trees, right? And again, this should come as no surprise. It's a binary tree of height h if all nodes at level h-2 have 2 children each. Okay, and when a node at level h-1 has children, all nodes to its left have 2 children at the same level. And when a node at level h-1 has 1 child, it is a left child. And I leave it to you to convince yourself that the slightly more formal definition is equivalent, if not identical, to this definition. Okay. Now we've introduced the concept of a full tree, we've introduced the concept of a complete tree. You've seen that all full trees are complete trees, but all complete trees are not full trees. Yes? You appreciate that? As given the couple of examples I said. So now let's introduce the notion of a balanced binary tree. And in some ways, a balanced binary tree is simpler than a full tree and a complete tree, in the sense that for no node, a tree is balanced if the heights of any node, its subtrees, 2 subtrees, differ by no more than 1. So you pick any node at random, and the height of the 2 subtrees hanging off that node may not differ by more than 1. And so if that is the case, it's a balanced tree. And again, you can see how intrinsic the notion of height is in the definition of balance. So now let's try to understand the relationship between full trees, complete trees, and balanced trees. I'm not sure how best to prove this, but I hope you appreciate the fact that all full trees are complete trees, are also balanced trees. Yes? I.e., every full tree is also a balanced tree. Every complete tree is a balanced tree. However, every balanced tree is not a complete tree, and every complete tree is not a full tree. Okay? And one last statement, which is nothing new. All full trees are both complete and balanced. Okay? As I said, I don't know how best to prove this. If you appreciate the definitions, this is almost obvious. And if it isn't obvious, please work it out. It should be. Any questions before? Okay, so here's an example of a complete binary tree. And as we've just said, this should also be balanced. I urge you to convince yourself that there is no node which has 2 subtrees of heights differing by more than 1. As a matter of fact, this is the only subtree where the heights of its subtrees differs by more than one, or differs by one, beg your pardon. Okay. You could say that, so I apologize. This is one, but these are two subtrees as well, right? Of this node, which has a height difference of one. So, okay, you get the idea. This is a balanced tree, and it's a complete tree for the reasons we discussed earlier, but you can see it is not a full tree. Okay, so now let's move away from the kind of structural properties and get quantitative. Let's try to answer some quantitative properties of trees. And quantitative here is what is the maximum and minimum height of a given binary tree? Okay. And then we'll also ask what is the maximum and minimum number of nodes in a tree of a given height. So two versions, or two different questions. What's the maximum and minimum height of a binary tree? And then what's the maximum and minimum number of nodes in a binary tree of a given height? Okay. So almost self-evidently, the maximum height of an n-node tree, n-node binary tree is n, right? And you've seen examples of this. This is a binary tree, right? Parent, child, child of a child. And therefore, if the value of n here is 3, what is the height of a binary tree of n with n nodes? It's 3, right? And that's because in this case the binary tree really results or reduces to a linear single chain. Is everybody with me? So the maximum height of any binary tree, quite evidently, is 3. But you can see that this is the, if you will, the maximum height of an n-node tree. But notice that the number of nodes is increasing. However, the height is not. So clearly for the same height, and I think you know this by now, you can have different number of nodes in a given tree. And therefore this begets the question, what is the maximum number of nodes you can have in a tree of a given height? Is everybody with me? Right. The height is the same, but the number of nodes is different. And therefore the question is, what's the maximum number of nodes you can have in a tree of a given height? Question.
It's on the previous slide.
Previous slide as in this slide?
Yes.
Yes.
Is tree A balanced?
I leave it to you to answer. Is it balanced?
I think it is. It looks odd, but I think it is. Because I think from the definition, the last node only has, or the middle node only has a difference of 1. And the one before it only has a difference of 1 from 5.
So what is the definition of a balanced tree? Its left subtree and right subtree of any node should not differ by more than 1.
Right.
So what is the height of the left subtree?
It's of the left subtree.
Yeah.
It's
Of this node.
That it's 3 if 1%.
No, the height of the left subtree is 2.
Oh, that's right.
What is the height of the right subtree?
0.
0.
Okay, so no, it's not balanced. I was just curious.
But no, your question is a very good question. But the point is, do you see why it's not balanced? That's what I'm trying to convey.
There has to be another node on the other side to balance it out, right? So like if it was weights, I guess this side is too heavy.
So this, right, so this is balanced.
Yeah, B is balanced.
This is balanced, this is balanced, this is balanced, and this is balanced.
Right, exactly.
This is the only non-balanced tree for the reason that the right subtree has a height of 0. The left subtree has a height of 2. That's more than.
Right.
Okay, good question. So as we just motivated before the question, how many nodes can a tree of a given height have? And again, I think you should be able to appreciate the answer because the question is for a binary subtree, it's not for a general tree. A binary subtree has, a binary tree, beg your pardon, has a specific property that each node can at most have 2 children. And so almost immediately you should say that, ask the question, a full tree is going to be a tree of a given height that will have the maximum number of nodes, right? Because it's full, right? But how many nodes can a full tree have of height h? Well, let's do the maths. So if you have height, let's say, so we're going to do this at the number of nodes at each level, and then we're going to add them up, right? Again, so for some of you, this will be quite obvious. For height, for level 1, I'm talking about level, not height. For level 1, what's the maximum number of nodes you can have? Well, 2 to the power 0, right? So that's really n 2 to the power of, so you can have 1, which is 2 to the power 0, right? And so at level 2, you could have at most 2, which is 2 to the power 1. At level 3, you can have 4, which by the way is 2 to the power 2. At level 4, you can have 8, which is by the way 2 to the power 3. So you can see that at any level, the maximum number of nodes that you can have at any level is 2 to the power level minus 1. And the minus 1 is bound to the level and not to the 2. I 2 to the power level minus 1. But you know that the maximum value of the level is the height, right? Go ahead.
So I was just talking to someone that's watching the live stream, and it's on slide 1 of your slideshow.
Slide 1.
I don't know if it's not updating.
It's probably got a delay.
But that's too much of a delay. Slide 1.
Okay.
Still on screens. The second page.
Need to freeze that.
No, the Hangout shows as every time I change, it also changes. Not sure what to do because I mean, is somebody connected to Hangout on there? Can somebody see here? Because for me, it should be working. But thanks for pointing that out, Nicholas. I guess just want to see if that is his or her problem or if it's.
He said it's fixed.
It's fixed.
Yeah.
Okay. So maybe I won't do a complete screen share. Well, that's not going to help. No. So I am going to try something. I don't know if this is going to help. Or if this is just going to confuse matters. If you get any feedback, let me know what feedback. Okay. Let's hope this works. And if somebody is also on Hangout. No, I can come up with. This is on the. What's about, right? Let me just hold on. That's fine. There's a bit of a delay, but let's see.
Well, YouTube is so Hangouts should be less because it's nothing from Hangouts to Google, right? To YouTube.
Yeah.
Yeah. So the delay.
It's not changing every time I change.
I think when you go to both screens.
Yeah, I think that's so. I'm gonna just to be good to our colleagues. Just show me what's happening there, please. So. Thank you. So it's still not changing. Still not changing. Okay, so not sure what's happened there.
Audio too. The audio is good. I heard what you said like a minute ago. So it's fast.
And there's a lag.
Yeah.
Okay, so I see things are changing now. Okay, so folks who are here, I'm going to apologize. I'm not going to go into full screen mode and just try to work off this. Is this too disruptive? Is this manageable?
You can make it bigger within this as well. I think the bottom, right?
Okay. Good point. Okay. Anything but full screen, right? Is this good enough for the moment?
Yeah. Says thank you, by the way.
That's the least I could do. Okay. So let's go back a couple of slides. So yes, so where we work through the equations, the form of the equation that is at any given level, the maximum number of nodes that you can have is 2 to the power of h minus 1, right? So now comes the mathematically interesting property of what is the maximum number of nodes that you can have at all levels in a tree, at all levels, including the last level. The answer is quite simple. This plus this plus this plus this, right? Because this is the maximum value at any given level. So at this last level, what is the maximum number of nodes you can have at all levels, including the last level? Well, it's the sum of these terms. And if you do your maths properly, it's 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, blah, 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 all the way to 2 to the power of height minus 1 plus, right? What is the value of 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 all the way up to 2 to the power h minus 1? Well, you should know this. It's 2 to the power of h minus 1, and now the minus 1 is bound not to the h, but to the 2. Okay, so 2 to the power of h minus 1 as opposed to 2 to the power of h minus 1. Okay, everybody appreciate the difference, and I hope people who whom this is being streamed. So that tells you something, that the total number, the maximum number of nodes in the full tree, in the full binary tree, is 2 to the power of h minus 1. Now let's have a look. Let's look at a couple of examples and see if this makes not only mathematical sense, but this is intuitive sense as well. So let's look at the most simple example. Let's take this tree. Okay, what's the height? 3. Therefore, what is 2 to the power 3 minus 1? 7. So the maximum number of nodes that a tree can have, a binary tree of height 3 can have, is 7. 4 plus 2 plus 1 is 7. Again, almost commonsensical, almost trivial to do the same for a binary tree of height 4 and 5. So how many nodes just randomly can a tree of height 10 have? You can either give me the number or the formula. 1, which is 1023. 2 to the power 10 is 1024 minus 1, 1023. Right? Okay. Everybody with me? Okay, so now let's move on. So we went to appreciate the maximum. So in a way, okay, so we've done the maximum, but I think we've also done the minimum, but let me just call that out explicitly. What is the minimum number of nodes that a tree of height h can have? H, exactly, the linear structure, right? So the range of nodes in a binary search tree of height h can be anywhere from h to 2 to the power of h minus 1. Okay, so broad range. Okay, so in a way, I've worked through all of this, so now I'm just going to kind of almost speak this out or read this out, because at this stage, these should be self-evident. A full binary tree of height h, where h is greater than 0, has 2 to the power of h minus 1. Sorry, this should have been on all together on one line. And I think we've just worked this through. A full binary tree, maximum number of nodes, and you know the maximum number of nodes is 2 to the power h minus 1. You cannot add nodes to a full binary tree without increasing its height, self-evident. The maximum number of nodes that a binary tree of height h can have is 2 to the power h minus 1, almost the same as this. The minimum height of a binary tree with n nodes, this is the interesting thing. The minimum height of a binary tree with n nodes is log base 2 n plus 1. Right? Note, earlier we were talking about minimum number of nodes in a tree of height h. Now we're asking a different question. We're asking the minimum height of a binary tree with n nodes. When does this happen, by the way? When do you get a minimum height of a tree with n nodes? When the tree is a full tree. Yes. And therefore, given the relationship that 2 to the power of h minus 1 is the maximum number of nodes that you can have, therefore, the value of h, so if n is maximum in this scenario, then if you take the log on both sides, you get h that is the minimum, right? And so please appreciate this. Okay. This is just kind of trying to appreciate the last few slides in a different way, where you're filling in the last level of a tree. Okay, so we've introduced the structure, height, level. We've talked about min, max, number of nodes, height. And now let's talk about traversal. Again, a very important property of trees. And no surprises, we're going to take recourse to a recursive definition of traversal. I think we've talked about traversals before in a different sense. But let's define the 3 different types of traversals that you can have in a binary tree. Remember, there's a special, so first of all, we'll take the recursive definition, and then we'll start with the special node that is the root. And the 3 types of traversals arise as a consequence of the order in which the root is visited relative to the left subtree and the right subtree. So just forget all of this. Think of what I've just said. It's the relative order in which the root is visited compared to the left and the right subtree. So one way would be to visit the root first, and then the left, and then the right subtree. That's type 1. The next one would be to visit one left subtree, the root, and then the right subtree. And then another way would be to visit the left subtree, the right subtree, and then the root. Okay. So I repeat, root first, then the left and the right subtree, root in between the left and the right subtree, and then the root after the left and the right subtree. So special order. And by the way, that's how you come up with these 3 terms, the 3 concepts: pre-order, post-order, and in order. Just to be more specific, you visit the root before visiting any of its subtrees, and this is done recursively. Okay, so you visit the root, and what does visit mean? In this case, do the operation, print the value, or just read the value, whatever it might be. We talked about visit in a different context. In order is you start with the left subtree recursively. Once you finish the left subtree, then you do the root, and then you do the right subtree. Okay, i.e. you visit the root in between the subtrees. And post order is when you visit a root after you visited both the trees, again, recursively. Okay, so I'm not going to work out the algorithms, but again, I just put the pseudocode here only to reinforce the recursive nature of these calls. Right? At this stage of the game, I don't think I need to point out that pre-order calls pre-order, right? And you understand what's happening. Okay, so you can see the bit. The first route is the route is first visited, and then two pre-orders, left, right. And then you can do. So now let's actually look at this in action. So we're going to do one. We're not going to do too many of these. Let's look at traversals of a binary tree. Let's pick, let's say, this tree, and let's do a pre-order, and then might pick one more. And these numbers indicate the order in which a tree, a node is visited. Right? So if you're going to do pre-order, you visit the root first before visiting the left subtree and before visiting the right subtree. So you start here. So you print out the root, 60. Then you visit the left subtree, which is this entity. Sorry for those who are, again, seeing this string. 20 is the root of the left subtree. So you print that out, right? And then where do you go? Do you go left or do you go right? Go left. Right? And again, 10 is the root of that subtree, but it so happens to not have any subtrees. Okay, so then you come back to here and then you visit the right subtree here. So you get a sense 60, 20, 10, 40, and you can go on and do 30, 50, 20. And that's the order. And again, I leave it to you to similarly appreciate the trace of the post order as well as of the in order. Okay? Question?
Just really quickly, looking at the trace of the in order, isn't there sort of like a forced misordering? Like, so you start
a forced misorder.
Okay, so you start out, you go 10, and then you go to the root, 20, then you go to 40, but 40 is the root of that subtree, right? So you're visiting the root, and then...
No, but it's, sorry, maybe it's 10, 20, 30.
Oh, I'm sorry.
Yeah, sorry, I can see the granularity. It's 10, 20, 30, 40, 50, 60, 70. Okay, so yeah, we just worked one more out. Thank you. So please work out the post order. Okay, and so no surprises, in order algorithm, post order algorithm. Again, notice the difference between the in order and the post order. Right? They're both recursive, but notice where the visiting of the root is relative to the recursive calls. Yes? Okay. Okay, so what are so now that we've set everything up, what are the kind of operations that a binary tree must support? In some ways, this is exactly how we were setting up our study of queues and stacks. We first looked at the kind of operations or the kind of things you do with them, and then we tried to define the basic operations that any ADT that was a stack or a queue must support. Here we've taken about an hour because we didn't know the kind of things you do with trees, but now you know the kind of things you're going to do with trees. That's why now we can start defining the kind of operations that any ADT tree should support, binary tree should support. Yes? Is everybody with me? Okay, so now what are the kind of operations that a binary tree should support? Well, the first thing is that a binary tree should test you, very similar to earlier, whether it is empty or not. No surprises, get the height of the tree. No surprises, get the number of nodes in the binary tree. No surprises for a given node, or well, in this case, the root, get the value of that root node, set the value, right? And then possibly add a node. Notice, again, notice what I said at the very start of the lecture is you don't say, what is the value of the 17th node? Okay, and okay, there's some more operations on the next slide, I believe. Right? So see, you have remove all the nodes, retrieve a specific entry in the node, but it's not captured by the 17th entry because the 17th entry may not mean anything. It might be the last entry, it might be the first entry, i.e. the root, okay, or it could be the left child of a given node, right? So remove the node containing a given data item from a binary tree, so you have to search for that. All nodes from a binary tree. You've said a specific entry, but not given by value, by the value of its position, beg your pardon. A binary tree contains a specific entry, so this is a search. And then another operation is traverse the entire binary tree in a given order, pre, post, or in order. Okay, so these are the set of operations which binary trees typically support. No surprises, again, along the lines of what we've done earlier. This would be a UML representation for a class that would be binary tree. I hope you remember the notation. We've kind of talked about each of these functions that any binary tree should support. Okay. So now this is a good time to revisit or now start thinking a bit more in detail the concept of a binary search tree. I've defined what a binary search tree is, but before we motivate a binary search tree, let's motivate a binary search tree before we talk about what is a binary search tree. And you saw on slides earlier that you often have to, in a binary tree, search for an item. Okay? You're looking for the value, let's say 42 in a binary tree. What is the cost of a search in a binary tree of let's say, size n typically going to be? What is the average cost of a search in a binary tree? Come on. Please. Sorry? No. In a binary tree. So how would you search in a binary tree?
You have to go looking for each single node.
Exactly. Because there's no ordering between the nodes, right? So sometimes you might be very lucky and it might be the rule, but as we discussed in a different context, sometimes you'll be very unlucky and it'll be the last node you look for.
Worst case is
So for n, the worst case is n, the best case is 1, but what's the average case? This is the non-trivial part.
Are you looking just for like the order?
Yes.
N?
It's still n, right? And you have to think, why is it still n? I mean, in some ways it's very simple, right? Come on, go ahead.
Because like you would add up the worst case and the best case, and then you would divide by 3, and then that would be.
In this case, yes, exactly, because if you were doing a probability distribution, you'd find that the probability of the number of searches that you would make with equal probability could be anything between 1 and n. Right? And therefore, you could just take the average of 1 and n. Right? 1 search versus n searches, and therefore n by 2. Right? Okay. So it's a simple explanation, but it's worth mentioning because we'll need to contrast this when we start talking about binary search trees and the number of operations. Okay, so let's move on. So search is very difficult when you have a binary tree. And as we've just discussed, and as you guys have proven for me, the cost of a search on average is order n in a binary tree. We are motivated to ask, can we do better? Right? Can we do better when searching for an item? Can we do better than order n? And the answer is yes, we can. And the answer and the details of how we can reside in the way in which we're going to construct a binary search tree, or how we define a binary search tree. And I'll just read out so I don't screw up this time. Binary search tree such that you now have not an absence of any order like a binary tree, but you have some level of ordering. Again, it's not as strict as a properly sorted array, right? It's just trying to say that n's value is greater than all the values in the left subtree, n's value is less than all the values in the right subtree, and both the left and the right subtree are binary subtrees because of nature. So we've seen this as an example before. We will now see this as an example. So you can see that this is a binary search tree because the properties are observed of a binary search tree. This has a left subtree, this has a right subtree. We've seen before that this left subtree is also a binary search tree. Note, the right subtree is also a binary search tree because to the right of Nancy is Tom. Tom is greater than Nancy. To the right of Tom is Wendy, and Wendy is greater than Tom, which by definition is greater than Nancy, which by definition is greater than Jane. And so you can see that this is a binary search tree. Clearly, it's not a complete search tree. Clearly, it's not a full binary tree. As to whether it's balanced or not, we will get to in a few minutes. So you've already appreciated one thing, that binary search trees do not, like any binary tree, does not have to be full and does not have to be complete. Okay. So all binary trees, so true or false, all binary trees are also binary search trees? True, false? All binary search trees are also binary trees? Great, thank you. Okay, and here's a classic example of this being a binary search tree, where you can see that because all the nodes, all these nodes are to the right of Alan, which means that they must all be greater than Alan, right? And you can just demonstrate that, verify that. Okay. Okay. And here's another binary search tree with the same data as figure 15 as the previous slide. So let's look at this. Alan, Bob, Elisa, Jane, Nancy, Tom, Wendy. Okay. And this is the binary search tree. And lo and behold, exactly the same nodes, but a different organization. Okay. Is this a binary search tree? Let's verify that. If it is actually a binary search tree, everything to the left of Tom should be smaller than Tom. Is that the case? Jane, Nancy, Bob, Alan, looks like that. Everything to the right of Tom should be greater. Wendy, kind of okay. And you can see that therefore this is a binary search tree, a valid binary search tree, i.e. the binary search tree property holds here. So you can already see that for the same data, you can have more than one binary search tree realization, right? Does everybody appreciate that? For the same data, you can have a large number of binary search trees. And this goes, and so the question is, what's the difference between this binary search tree and the binary search tree on the previous page? Does somebody want to tell me what's the primary difference between this binary search tree, which is of the data that we've discussed, being the same as the data here? What's the difference between this binary search tree and that binary search tree?
Certain items are going to take longer to find.
Say again?
Certain items are going to take longer to find than one versus the other.
That is correct. And what's another distinction? Go ahead, please.
Is it like the linearity, like one is linear? and the other one is-
Correct, but what does that translate to? What's the general remark I'm trying to look for?
The heights are different.
Exactly. The heights are different. So you can see that binary search trees, even when you can construct it from the same data, can result in trees of varying / different heights. And this gets to the root of an important problem is you want the advantage of binary search trees because we said that binary trees are order n and therefore inefficient when searching. We proposed binary search trees as a way to overcome that deficiency. We haven't proven what the cost of a search right now is. We'll get to that in a minute. But we then realized that there is a problem. We don't have an order n cost necessarily, but we could possibly end up with very different structures for our binary search tree, which in the worst case could end up being order n. And if it is order n as the height, if the height is n, then the cost of a search will be order n, which then makes it no better than a binary tree. Does everybody see what I'm trying to say here? We set out to solve a problem of inefficient search in binary trees. We claim to have solved that with this, introducing this ordering, this partial ordering. Everything to the left, in the left subtree is smaller than the node, everything to the right is greater. But then we see how for the same data, you could end up with binary search trees of very different heights. And you saw one example where everything was linear, a chain, i.e. searching would again reduce to order n. Yes? And so you can see, therefore, our problem resolution requires not only the ability to create partially ordered binary search trees, but also the necessity of keeping them from becoming linear chains. We want to prevent them from becoming linear chains, i.e. we want to keep them as close as possible to being full trees or complete trees. Does everybody get the logic I've tried to lay out, the motivation for what we're about to get into? Go ahead, Bob.
Question. So from this diagram, we can see that Nancy's greater than Jane, which is to the right. And then Tom is also greater than Jane because she inherits from him, right?
Jane is less to the left of Tom.
Right, yeah. So then Tom is bigger, right?
Yeah.
So, but what you don't know is necessarily Tom's relationship to Nancy.
You do?
Or is it that because it's lower, even though it's in the same ranking, because it's lower, then Tom is bigger?
So you have to think recursively here.
Right.
Everything to the left of Tom, everything, not just the top node, not just Jane, but everything in the left subtree must be smaller than the node, i.e. Tom. Okay? Everything to the in the right subtree, everything must be greater. Now, something that is smaller than Tom but greater than Jane must reside in the right subtree of Jane, because by definition, anything that is a subtree of Jane will be less than Tom by definition, left or right, but something that is greater than Jane must reside in the right subtree. And therefore, Nancy is greater than Jane, less than Tom by definition. Okay, great. Okay. Okay. So again, what are the operations that a binary search tree should support? Whether the binary search tree is empty or not, very similar to earlier. Get the height of the binary search tree, get the number of nodes in the binary search tree, get the data in the binary search tree's root, okay? Insert, remove, okay? And similarly, remove all entries from a binary search tree, essentially destroy it, retrieve a given item from a search tree, okay? And then traverse, in this case, pre, post, and in order, okay? So the most fundamental algorithm, the most fundamental operation that you perform on a binary search tree, no surprises, is a search. Okay? As I tried to emphasize, the whole raison d'etre of a binary search tree was to try to support efficient searches. Now, having said that, it should come as no surprise to you folks as to how to implement a search algorithm on a binary search tree. We've done this in class in 4 different contexts, right? So who's going to tell me, spare my voice, as to what the binary search algorithm is? You look very eager to answer the question. Yes, you.
Binary search.
Yeah.
So you start in the middle.
Yeah.
And compare that.
The middle, no, in this case, you start at the root.
compare that to item you're searching for. If the group is greater than the search item, then you go to the left subtree.
Correct.
Otherwise, it's the right. Okay, person keep repeating until you either find it or you don't.
Very nice. Until you find it or you don't find it. I think that's the crux of the point here. If you find it, very good. Okay. If you don't find it, what do you do? Well, we'll talk about that in a second. So let's just talk about the cost of finding it. But before that, does everybody understand the algorithm, the binary search algorithm? As I said, we've done this in different contexts, so it should be really no surprise as to what the binary search algorithm is. And you can see that the binary search tree, its whole design, its whole construction is such as was by design was created to support a search algorithm efficiently. So what does efficiently mean? What is the cost of a search algorithm on a binary search tree? Somebody? Log n, and that is because, go ahead.
Because like at most, you only have to traverse like the height.
Exactly, thank you, that's what I was, and the height of a tree. Okay, so we have to be careful. There's a worst case, there's a best case, there's an average case, right? In the worst case, we know it is order n. In the best case, it is what? Traversal of the height. What's the height in the best case? So you're right, in the search might be order 1, right? Because you find it at the very first go. But the height would be? So the height on the traversal height is something.
Are you looking for the best case? Like,
Yes, what would be the best case of the height? Which really is the lowest value of the height. Right? So, log base, log n, right? Did I confuse things? No, are you with me? So let's step back. Try to determine the cost of the search operation. We know that in the best case, as you said, it might end up being 1 because the first item you look for is the item you need to find. Okay. In the worst case, it would be n because a binary search tree could end up having, in the linear case, it could end up having n. The question is, what's the average? And the average, as we've seen, is log n because the average height would be log of n. I've just said something, and I hope you all appreciate that the average height of a tree of n nodes is going to be log n. We've done enough math that it should be quite obvious, but appreciate the fact that I'm talking about the average height. It should be log of n. And we'll actually spend some time discussing this property, why it's not h minus, why the average height is log of n, obviously base 2, and not some other value. Okay, give me a second, searching a binary search tree. So we've seen this before. So now let's come back to the point that was made a short while ago. What if you don't find the value? You're searching in a tree, but you don't find the value. Okay, the item that you were looking for was not in the binary search tree. But what you have ended up finding is the location in the search tree, in the binary search tree, where if that item had existed, where it should be found. You do not find it because it doesn't exist, but you found the place, the right place in the binary search tree where you ought to place that. And therefore, the search algorithm becomes the basis for an insertion of a node into a binary search tree. We'll repeat that one more time. You look for an item, in this case, let's say Frank, and you perform your binary search, and you end up at the end of the tree on the leaf node, which by definition cannot have any more children, but the leaf node is not Frank, it's Elena or something else, and therefore you failed to find Frank. However, had Frank existed, you would have found the position because you know either to go left of Elena or right of Elena. Right? So turn this around, and you can now answer the question that if you had to insert Frank, you would perform a search for Frank, and then at the last step, you would then determine whether to put it to the left or the right of Elena. Right? So basically, what I'm trying to tell you, the search algorithm that we just talked about is used not only for search, but it's also used for insertion operations. So the insertion is just a wrapper and then some around the search operation. And then you can, if nothing else, it just reiterates the importance of having an efficient search algorithm and hence the binary search. Notice, I have not discussed delete yet, right? I said insertion, but I didn't say deletion, and we'll talk about deletion in quite a bit of detail because the situation there is slightly more complicated. Okay, so traversals of a binary search tree, no surprises, in order, post order, pre-order, you should be able to figure that out. The algorithm's there, as a matter of fact, identical to earlier algorithms for just a binary tree. Binary search trees are binary trees, no surprises there. Okay, so up till now, I hopefully have convinced you that in the worst case, in the binary search tree, all operations are going to end up as order n for the reasons that you now know, because of the fact that the binary search trees may end up being unbalanced. But I've convinced you that the average case is log of n. Okay? And all operations that actually use the search operation, there may be wrappers around the search operation, but they all end up being in order of ordering. Okay. So something very quick, and then we'll go into discussing deletion. Right? Let me just see what's the time. Yes. So there's two things we're going to do. I'm going to say something very quick about the structure. About the implementation, and then I'm going to talk to you about how to perform a deletion in a tree, in a binary search tree. So no surprises. The implementation of a tree, so happens to be binary tree, which then so happens to be a binary search tree, can, like all of the ADTs, can be either link-based or array-based. Right. Even before we go any further, can somebody tell me what's the problem with an array-based approach? Okay, go ahead, please.
An array-based implementation kind of lends itself to a linear kind of ADT, and the trees specifically on that.
And correct. And so what happens? I mean, in a tree, what you want, if you think about the operations in a tree, what you want is a very quick way of finding the child, the root of the left subtree or the root of the right subtree. And you can see why an array is not the right structure for that, right? Because the array gives you physically adjacent, right? But physically adjacent may have nothing to do with left or right subtrees, right? So if you use a linear structure, you have this problem of determining what's the child. Did you have a question? Thank you. So we need to be a bit more careful. I've given you a hand-waving argument. It conveys the point, but there's something slightly more subtle when thinking about arrays as a representation or as an implementation for these structures. We will not get into them, into the details of array-based representation, for the simple reason we won't actually ever use array-based approaches to capture regular binary trees. We will use link-based approaches to capture regular binary trees. That is not to say we will not use arrays for binary trees at all. We will use arrays for the special case of complete binary trees. Please note, for the special case of complete binary trees, we're going to use arrays. And just picking up from the earlier observation that the problem with arrays is that you don't have a nice ordering of parent and child. With complete binary trees, that constraint is removed. Because of the property of complete binary trees, where you know that they are full to level h-1, and importantly, in the last level, i.e. level h, they always grow, or nodes are always added from the left onwards. As a consequence of that property, you can use the index value of an array and have a simple operation on that to get the value of the child or the parent. Okay, and we'll see an example of that. So that's when the tree is complete, when you have a complete binary tree. However, for the general case of a binary tree, where you perform a large number of insertions and deletions, the representation using an array is quite complex for the reason that was pointed out. You have to keep not just the values of the arrays, or of the nodes, beg your pardon, but you have to do a fair number of operations to determine which is the left child and the right child, because you'll go through a series of insertions and deletions, right? And as a consequence of insertions and deletions, these values might change. So again, I urge you to read about it, but I also kind of convince you that you don't need to worry about array-based implementations. But this is what I was trying to say. An array-based representation of a complete binary tree is efficient, is memory, and also both in terms of the operations. And we'll come back to this in a short while. But I just want to kind of make sure I leave a marker about that. Okay, so sorry, we're actually going to talk about this right now. So look at this. So this is a complete binary tree. I think you all appreciate that. And notice we've got Jane, Bob, Tom, Alan, Ellen, and let's look at this. What's the relationship between Bob and Ellen? Well, Bob is Ellen's parent, right? Where's Bob here? Bob's value 1, sorry, array index 1. Ellen is value index 4. So what I'm telling you is that to determine the child, the right child of any node in a complete binary array is trivial. It is 2i plus 1. So if I is the value of Bob, sorry, 2i plus 2, beg your pardon. So if Bob is the parent, has an index value of 1, its right child, Ellen, will be in position 2i plus 2, i.e. 2 into 1 plus 2. And its left child will be 2i plus 1. Let's look at that. So we're now going from parent to child. 2i plus 1 is 2. So remember, this is index is 1. So 2 into 1 is 1. That is 2. Plus 1 is 3. And that index value is Alan. So all that's very easy to go from a parent to a child. But can you go back from a child to a parent? Right? So is there a mathematical relationship? And it so happens, but before we go any further, let's just ask, does that hold in general? And the first best way to look at that is, let's see if 2i plus 1 gives us the relationship between Tom and Nancy. So Tom is in position 2. 2i plus 1 should be 2 into 2, 4 plus 1, 5. We should find an index value 5, Nancy. Okay? So you can see how trivial it is to go to the left child and the right child from a row, from a node, if you use an array for a complete binary tree. Okay? In the interest of time, because we're going to come back to this later, I'm not going to give you the mathematical relationship for how to go from a child to a parent, right? It's actually quite simple. I'm sure many of you can work that out, but we'll do that when we talk about heaps. Okay. For the moment, I just want to, for completeness, show you that once you are told it's a complete binary tree, it's very trivial to go from a parent to a node to a child in the where to look for the value of a parent child. Okay. Okay. So now I want to get to, as I said, having talked about the first part of how to find the relationship between a parent and a child for a complete binary tree, the next important aspect is the deletion algorithm. So what does deletion here mean? So you've got a binary search tree. Okay, so let's step back for a second. Maybe I should say one thing more. You know the search, we just talked about the search algorithm as at the core of an insertion. Why did you have to perform an insertion in that way? Well, remember, any insertion that is performed must preserve the binary search tree property. You can't just take Frank and insert it anywhere, because if you do that, you're going to break the binary search tree property, right? If you just took Cody in this insertion and you inserted Cody here, well, that's not going to work because you'll have broken the binary search tree property. K is greater than E, so clearly K should be to the right of Elisa, but K is less than Bob, sorry, K is less than Nancy, so okay, there's clearly two locations you could have had here. But let's say you had put K to the right of Alan, that would have been technically correct. But it would not have been correct because K is greater than Bob and therefore should not be in the left subtree. So there's a finite number of positions where you could insert Cody. And in order to insert Cody in the right place without violating or breaking the binary search tree property, you want to be able to do this, use a search-based approach. Okay, so the important thing is insertion cannot happen anywhere, to state the obvious. It has to happen in such a way that the binary search tree property is preserved. And this carries over into our deletion. As you'll now see that you can't, in the way we're going to perform a deletion, you can't just delete anything from anywhere and then hope that the binary search tree property is preserved. This is more complex, so we have to break this down into 3 cases. You want to delete a node, and that node happens to be a leaf, right? No problem. If the node is a leaf, you just remove the leaf. What happens to its children? Well, there are no children because it's a leaf, and you have no problem. Are you with me? So if the node that you need to remove is a leaf, I has no children, no problem. You just remove it, and you've preserved the binary search tree property. What happens if the node that you need to remove is not a leaf, but it has exactly one child? Well, you should then ask almost immediately, the node that you want to remove has one child. Is it a left child or is it a right child? And then what do I do? I'm going to argue that it doesn't make a difference whether it's a left child or a right child in what you're going to do, as long as you take the child of the node you want to remove and make it the child of the parent of the node you wanted to remove. I.e., you made the child now a child of its earlier grandparent, right? You are going to preserve the binary search tree property, right? Is everybody with me? And it doesn't make a difference whether it's the right child or the left child of the node you're removing, as long as you promote that to be in the new position of the node you've removed, you have preserved the binary search tree property. And let's actually look at this in an example, which is here. So you need to remove Bob. So you've got Jane, Bob, Alan. You need to remove Bob. What I'm proposing is whether you have to, and in this case, you have to remove Tom, which has a child to the right, sorry, to the left. This has a child also to the right, to the left. So you remove Bob and make Alan, promote Alan here, and you've preserved the binary search property, i.e., everything to the left of Jane has remained smaller. No violation. Similarly, here, if you remove Tom, even though it is now the right child of this node, as long as you promote Nancy to where Tom was, you've still preserved the binary search property, namely, if Nancy comes here, Nancy is greater than Jane, and therefore no violation of the binary search tree property. So again, this is quite simple. If you have n is a leaf, no problem. If n is a child, it makes no difference as long as n's parents, or in this case, right. So I should probably not have n prime, beg your pardon, it should just be n. N's parents adopt n's child. Okay. What happens when there are two children in the node you want to delete? You can almost ask, the algorithm that I had for one node, that's no longer going to work because I now have to arbitrate which of those nodes do I promote up. Okay? And the answer is, let's not use the same approach. Let's now say we're going to remove the node that we want, but we're not going to necessarily substitute that with one of its children. We're going to substitute that with another node such that the binary search tree property is not broken. The question then becomes, which node can that and ought that be? Which is the next, which is such an, find for me a node that I can place in lieu of the node I want to remove, and I do not break the binary search tree property. So it's not an easy question that I've presented. Question for you is, when a node that you want to remove has two children, how do I determine a node that I can use to replace the node that I want to remove without breaking the binary search tree property? Remember, you can't just remove it because you'll have lost the tree property, right? So if I give you an example here, this is an example of a node with two children, and I want to remove this. You can't just remove this and do nothing because you'll have broken the tree. You clearly have to substitute something here. And I just said, don't try to say, which of these two should I substitute here? Because there's no easy way to answer that. So what is the right way to answer that? And this is where traversals come in once again. So remember, we talked about in-order traversal, okay? And an in-order traversal needs to be performed such that the node I want to remove is substituted by the next node if I were to perform an in-order traversal. And if I get that node, the next node in the in-order traversal, and I substitute this node with the node I have encountered in an in-order traversal, I preserve the binary search tree property. Now, let's spend some time thinking about why this happens. I'm actually of the opinion that this is a very important discussion, and I can see people fading at 9:50. So should I pause here and pick this up tomorrow? Or would people like me to take this to completion? First of all, is everybody with me? Does everybody understand the problem I've posed? Yes? Okay. So maybe I'll just very quickly sketch this out, and then we can kind of do this in more detail tomorrow. So here's the problem. You want to remove Jane. You can't just take Alan and substitute Jane with Alan, because you'll have broken the binary search tree property, right? If Alan comes here, as you can see, this is no longer a binary search tree, because Alan is smaller than Bob, right? And that can't be the case. So you have to choose a node properly. And I guess what I'm trying to say is the only way you can substitute the node is to find the item that is greater than the node you want to substitute, but less than everything else. So its nearest neighbor in terms of value. So you want to substitute the node you're deleting with the next valued node, so that it is greater than the node you're removing, but less than everything else. Question?
Would it also be possible to move the first node on the left up, and then take the right side of that, what used to be that left node, and then just put it on the farthest left branch?
So
right
yes,
side?
I think I see what you're saying. You can take the node that is, as I was trying to say, the first node that is greater than the node you're deleting, but less than every other node, or you can take the first node that is smaller than the node that you're deleting, but greater than every other node, and substitute that. And if, and only if you do this, you preserve the binary search tree property. Question?
These nodes that you're going to substitute are going to be below this current node.
Aha, that's what we're going to find out. I'm just trying to say, what node can you substitute the node you're deleting such that the binary search tree property is preserved, right? And now we'll then answer the question of where can I find these nodes? Question?
Pretty sure you. So you're now saying that you can use a child, like one of the child nodes?
Yes.
Okay.
But not any child node. It has to be a specific child node, right? There's another question hand that was rising. Did you have a question? Okay, so let's pause for a second. You now understand we're trying to replace the node that we're deleting with an appropriate node, with a proper node, such that the binary search property is not violated. We've identified two possible candidates. The first candidate would be the node that is immediately greater than the node you want to delete, but smaller than every other node, or immediately smaller, but greater than every other node. And then is the question, where do we find these nodes? Well, this is where the in-order traversal comes in. If you perform an in-order traversal on a binary search tree, you end up either finding the next node in greater in value or the node right before in value. And this so happens to be, and let's think of where. So think of all the values in the right subtree are greater than the node. Once you find you're in the right subtree, where is the smallest value in the right subtree? It's in the leftmost, right? So if you go to the leftmost position in the right subtree, you found the item that is greater than this item, but less than everything else. Are you with me? And similarly, if you want to find the item that is smaller than the item, this node, but greater than everything else, you descend into the left subtree where you know everything is smaller than the node you're about to delete, but you want to find the maximum of all of these that are smaller than the node you node you want to delete, which is therefore found in the extreme right position. Okay, that answers the conundrum. You can substitute the node with either this, which is the extreme right in the left subtree, or this, which is the extreme left in the right subtree, and not disturb the binary search tree property. Okay? Does that make sense, everybody? I propose we pause here and pick up tomorrow and convince ourselves that if we do find these elements, so remember, 3 parts of the problem. Identify the characteristic of the node that we can substitute with. Second part is, where would we find this node with such a characteristic? And then to convince ourselves that if we do substitute, we will not lose the binary search tree property. So we'll pick this up tomorrow, and then we'll look at tree sort, and then we'll do heaps. Okay? Any questions? If not, thank you very much for coming out to the state. Have a good rest of the evening. Take care, all of you out there. Bye-bye.